an interesting problem. Let's do this. It's a linear algebra problem. Let's do some math. So A is a 2 cross 2 matrix, and determinant of A is 1. Trace of A is 3. So what is the trace of A square? Any ideas how to do this? What do you find? Yes, how do you find it?
So can you just give me a minute? A few of them are done. I'll just mark them. Please give me a minute.
This is done.
Yeah, just give me a minute. I'm marking it. Just give me a minute, please.
Okay, yeah, it's okay, sure. So for those who have not seen the problem or done the problem, let's try it out. So if A 2 cross 2 determinant is equal to 1, so what do you need to find out? Anyone wants to interact with me and get the problem solution without sitting there and watching me do the solution? Raise your hand.
A square's determinant is, oh, sorry.
Okay, someone has raised his hand. Just give me a minute. Yeah, please raise your hand or her hand. Ayan Khan, yeah, sure. Ayan. Please unmute yourself.
Sir, I think
So what's on your mind? How can you solve this problem?
Sir, I think since this is a 2 cross 2 matrix and it is
Yeah.
general, so we can consider just a general matrix and find A square, and I guess we'll have relations in A, B, C, D, and from there we can solve it, I guess. Because
Okay.
directly,
So
we
just
don't
it's
have.
called a bashing way. So just do and just do all of them. Okay, great. Any other ways out?
We can just
Yeah,
construct
Aniket.
a
Wait.
matrix
Please
with,
raise your hand before Raj Shankar. Please raise your
yeah,
hand.
such.
No worries. Okay, yeah, Aniket.
Yeah, I was thinking like if there is a property like if we consider that A's eigenvalues are lambda 1 and lambda 2, then the A square's eigenvalue will be lambda 1 square and lambda 2 square. So lambda 1 plus lambda 2 is equal to 3, and lambda 1 lambda 2 equal to product of the is 1.
Very good. Super.
Now,
Yeah, that's the way out. Okay, that's the way out. Not doing the entire thing. Okay. So just the basic idea is that A to the power n ka eigenvalues are like if A has eigenvalues lambda 1, lambda 2, lambda k, then implies that A to the power n eigenvalues are lambda 1 whole to the power n lambda. And therefore you can use the determinant as lambda 1 lambda 2 equal to 1 and lambda 1 plus lambda 2 equal to 3 to find out lambda 1 square plus lambda 2 square, right? It's basic algebra. All of you got it? Yes or no? Rajshankar, you had the same idea or you have some other thing in your mind?
No, that was what I was about to.
Okay, that's great. If you understood, please reply yes in the comment box. It's very important for me to understand if the students are understanding or not. Okay. Okay, so are all of them marked, SK?
Yes.
Okay,
Yes.
thank you. Okay, let's do another linear algebra. So A is n cross n. Are non-zero eigenvalues, then which of the following are true? Let's see, no, distinct. Yeah. If A to the power n has r distinct non-zero eigenvalues. Rank of A less than equal to r. If r equal to 0, then rank of A is less than equal to less than n minus 1. So which are the following? Let's start with the last one because it's similar to this previous one. What do you think about this? Is it true or false? What do you think about this? True. Are you sure, Shukrit? Why Vamshika? Why Shukrit? Why it's yes or false? No. Yeah, Vamshika?
So because one of the, I mean, two eigenvalues could be n and minus n, and then
Very good.
the square.
Good. So it can have -1 and 1, and it can become 1 after squaring. Okay. So therefore, this is not true. Very good, guys. So what about this? So it's all about rank. Okay. Now you have to map eigenvalues to rank. Understand that. So therefore, the basic idea when you're doing MCQ or MSQ is that you group up the problem MCQ, the group up the you group up certain options to see what they're looking for. Here they're looking for rank relationship and eigenvalue relationship. Here they was looking with square and eigenvalues. So this is called batching. Okay, so it's a very good important idea in productivity. So we batch up the options together and just solve that problem. So this is where how you have to do MSQ to quickly batch up the options together. So okay, so what is the relationship with rank and eigenvalues? What is the relationship with rank and eigenvalues? Any idea? Yeah, Ayan?
Sir, one of the ways we could connect the two is that rank is related to determinant, and determinant is related to rank. Determinant is related to eigenvalues being zero and non-zero. So that way.
You're right, but understand. Just give me a minute. Just let me check the problem once. R elements. Yeah, you're right. So one way to is relate to determinants and yes, you're right. So that's what I told you, that if all eigenvalues are non-zero, then it's y, because all eigenvalues are non-zero. Determinant of A is equal to product of eigenvalues. So it's equal to if any 0 implies rank is less than n. If any non-zero, rank is if all non-zero, rank equal to n. That's great. So if you observe, this is asking r. So this two are asking about r, but this is asking about n. Okay, relationship with n, right? So therefore, another two options are there. Like if r is equal to 0, if there are zero distinct non-zero eigenvalues, if all of them are 0, right? If all the eigenvalues are 0, then is rank less than equal to less than n minus 1? What do you think? If all of them are eigenvalues 0.
All of them are zero, then it's a nilpotent matrix.
Yes. So is rank less than equal to n less than n minus 1? We know rank is less than n, but is it less than n minus 1?
No, it can be n-1 as well. If you
How
construct
can
a
you give an
basic
example?
we can construct a 2x2 example stating it row wise.
Yeah.
1 1 0 1.
So let's find out eigenvalues. It's 0 1 0 1 0. Sorry. Determinant. Yeah, great. So yeah, the eigenvalues are 1 here. Yes, sorry. I think if you do it zeros, then it's fine. And then it's lambda square. So therefore all eigenvalues, but you can see the rank is, what is the rank here? The rank is 1, right? So it can be n-1. All of you got it? That eigenvalues can all be 0. All 0. All. That implies, of course, rank is less than n. In fact, rank is equal to n-1 is achieved. Less than equal to n-1, it's achieved. So therefore, it's not less than n-1, okay? So therefore, this is also false. All of you got this option? Yes or no? What about others? Great. Now, therefore, we have got down the problem has boiled down to the aspect of rank relationship with number of eigenvalues, distinct non-zero eigenvalues. Okay. So now, can someone tell me what's the relationship with an number of non-zero eigenvalues?
Same example, we can strike down the first option.
Huh?
From the same example that we considered, I think we can strike down the first option. In this case, there are 0 non-zero eigenvalues. Sorry, there are 2 ones. I'm sorry. I'm so sorry.
So there's 0 non-zero eigenvalues. You're right. Oh yeah, you're right. So you're right. Yes. Yeah. So here r equal to 0 and rank of A is equal to 1. So it's greater than or equal to 0. So therefore this is also false. Thank you, Raj Shankaran. So therefore we get that rank of A is greater than or equal to R. That's good. But can you prove it right now? Yes, can?
So can you please repeat the last part? How we cancelled out the first option?
Oh, we just take the same example out here. A is equal to this. R is equal to 0, but rank is equal to 1. So this will not be true.
Okay.
Yes. So R is equal to 1. Sorry, what I'm saying. Rank is equal to 1 and R is equal to 0. So yeah, so how can you show this rank? I hope it's clear, Vangshika.
Sir, number of non-zero eigenvalues. We have two non-zero eigenvalues, right? 1 and 1.
Where? No, I changed the A, right?
Oh, okay.
Otherwise, this couldn't have been shown. Right. Okay. So why is rank is greater than or equal to R for R non-zero eigenvalues? What do you think? For R non-zero eigenvalues, distinct non-zero eigenvalues. No, the rest of the the rest of the can be non-zero too. You're right. Yeah, you're right. If all of them are non-zero, this of them the set of eigenvalues is this. Just give me a minute. I think I read the question wrong. Yeah, the set of R, the set of non-distinct eigenvalues, the cardinality of the number of non-distinct eigenvalues is R. That's it. The other can be the same too, like it can be 1, 1, 2, 2, like this also. But R is equal to 2 here for n equal to 4. So for R distinct non-zero, so I think someone raised his or her hand. I couldn't.
Yeah, I
Yes.
thought of something, but I'm not sure about it. After you
Please go
changed
ahead.
the question, I'm not sure. So there is this thing, right? So if we have R distinct non-zero eigenvalues, that means there are R independent eigenvectors. So that means they will span the vector space till R dimensions, right? So that's why it could be at least, rank should be at least R. I'm not sure
So why
about
do you
it.
say
Theorem,
that?
I just remember there is this theorem.
Okay. Why do you say if there are distinct non-zero eigenvalues, then the eigenvectors will be independent? Like there will be R independent eigenvectors.
I'm not sure it is about it is if and only if thing, right? Or it is just one way. I think I always get confused in this.
No, we cannot diagonalize. Yeah, you're in the right direction, SK. So we cannot get we cannot diagonalize the matrix here because it may not be diagonalizable, right? Great. So yeah,
Right.
think in the terms of as SK has shared, number of. So think about the number of non-distinct eigenvalues and the corresponding eigenvectors.
Sir,
Yes.
sir, I think that part is correct. That corresponding to R distinct eigenvalues, we'll have R independent vectors. We'll have corresponding to them the eigenvectors will be linearly independent, but it's not necessary there are.
It won't necessarily.
It's not necessary that they'll be R only. Corresponding to one eigenvector, we may also get to a set of two eigenvectors that are alike. I had done one question there. This was the case.
Okay, let's see. No, that's not the correct way, Gangathar. If a v1 is equal to lambda 1 v1 and a v2 equal to lambda 2 v2, so let's say alpha v1 plus beta v2 is equal to 0. That's a dependent. So we get, if you multiply like if you multiply by a, we get a lambda 1 p1 plus beta lambda 2 v2 is equal to 0, right? If we multiply this, so therefore we multiply by lambda 1 here and we subtract this, we get beta lambda 2 minus lambda v2 is equal to 0, right? This implies that lambda 1 equal to lambda 2, but lambda 2 1 is not equal to lambda 2. Also, we cannot have beta equal to non-zero, so it implies that v must be equal to 0, right? But it is not that eigenvector. So therefore, we can similarly prove that you're right, SK, and Shukri is also, Iron is also right, that if lambda 1 is not equal to lambda 2, then observe that v1 and v2 are linearly independent. And you can extend this proof by induction to n steps. Okay, we have done this proof. So therefore, you're right. N distinct eigenvalues, two distinct eigenvalues are at least one vector which are linearly independent to each other. Okay, so these are the eigenspaces. So eigenspaces, the eigenspaces are linearly independent. So this is the reason why. So the idea is that, yes, SK.
So can you repeat the thing once again? Like if we have r independent r distinct eigenvalues, then we have at least r independent eigenvectors, or just r independent eigenvectors?
At least.
Yeah, because we know at least there are at least r distinct eigenvalues.
Yeah, at least r distinct eigenvectors. You're right.
But if I know there are exactly r distinct eigenvalues, then there are exactly r independent eigenvectors.
So you know that the problem statement is they are distinct eigenvalues.
So it is not at least r.
At least eigenvectors are independent eigenvectors. Linearly independent. I'm not getting your question.
I'm getting confused.
Please go ahead.
There are at least r distinct eigenvalues, or exactly r distinct eigenvalues?
Exactly r distinct eigenvalues.
Okay, so exactly r distinct eigenvalues, that means at least r are independent.
Yeah.
Okay.
At least r distinct eigenvalues also means at least r distinct linearly independent eigenvectors, because you don't know how many are.
That is okay, but if there are exactly r distinct eigenvalues, that means at least r independent eigenvectors.
Yeah.
Okay.
So there's a proof of this, okay? There's a proof of this, so you can all find it out. Yeah. Okay, all of you got this, yes or no? I have shared a bit of a proof here, but you can just extend it. It will be n linear independent. R linear equations you have to solve. It's very easy to solve, just by Gaussian elimination. All of you got this problem, yes or no? Others? Yeah, Aniket.
I didn't just get that r equal how that I'm a bit confused. Like how r equal to 0, because if say for example you have taken an example where the eigenvalues are 0 and 0. So here
R
r
equal to 0
to
means
1.
all eigenvalues are 0.
No, here it's given r distinct non-zero eigenvector. That means if
Non-zero
in this case,
eigenvalues.
yes, non-zero eigenvalues. So the example you have taken, a equal to 0, 0, 1, 0. Here the eigenvalues are 0, comma 0, right?
Yep.
So only
So there is
one.
no non-zero eigenvalue. There's only 0 eigenvalue.
Okay.
The
So if
complement of, so there are zero non-zero eigenvalues means they are the only eigenvalues are zero. Understand?
Yes. Yes. Yes.
Yeah,
Now
it's
and now.
not logic.
Yes.
Got it?
Yes.
Great. Okay. Next problem. You can use geometric multiplicity. You're right. The proof of geometric multiplicity is, I mean, the idea is given here, like it's a similar idea. But geometric multiplicity is not in the syllabus, so you may avoid that. But it's a beautiful thing to learn. Yeah, we have not taught because it's not in syllabus. It's in the BSc Stat course, so they learn it. It's related to geometric multiplicity is nothing but the. So if actually I have mentioned this before, if AV equal to lambda V, then observe that V is nothing but belongs to the null space of A minus lambda I. This null space of A minus lambda I is a subspace, and if you consider the dimension, that is the geometric multiplicity of lambda. So essentially, the rank is nothing but the number of. So geometric multiplicity means there are, let's say it's G, so G lambda. So G lambda distinct eigenvalues. Okay. Like linearly independent eigenvalues, right? You can prove that. So therefore, there's summation of G lambda I from 1 to R eigenvalues, and G lambda I is greater than or equal to 1. Therefore, it's greater than or equal to R. Yeah. Did I do it correctly? Probably yes. Yeah, did you do it like this, Vanshika?
So what I did was कि geometric multiplicity is greater than 0. So it is greater than or equal to 1 for each eigen value.
Yeah. Yeah, that's
so
what I. That's,
this exactly.
yeah. Okay, fine. Great. Let's go to the next one. You're right. But yeah, it's not important. Like you can just do it by basic things also. Let's do an analysis problem. Okay. Let's do this analysis problem. So there are 3 series asked whether it's convergent or not. The first series is. The second series is. Third series is. Fourth series is. And if you remember in our Cheenta course, we have explained a lot and we have spent almost infinite time to explain how to solve this problem. The idea to solve this problem is order of n. That means you have to check the functions is of which order, like order of a function. So yeah, so that's the problem. That's the idea. It's asking that it's absolutely convergent. It's convergent. It's convergent. It's absolutely convergent. The question is here. Which the following are true. It's convergent. It's convergent. Okay. So just check it. Just let's do it. So if you just take the mode of, if you take the absolute convergence of it, it's nothing but 1 by root n. So is it convergent? 1 by root n? Is the summation of 1 by root n? Is it convergent? Yes or no? It's convergent. It's not convergent. So therefore, it's not absolutely convergent. Hence, it is not. Hence, it is not conditionally convergent too. Is it right? Yeah, SK?
No, sir. If it doesn't converge absolutely, doesn't imply it won't converge normally. I mean, without absolute thing. The given series will converge by alternating series test.
I'm getting
Because
you.
okay, the given series -1 raised to n divided by root n, it will converge by alternating series test.
Okay, so that's what I'm asking. I did a method. I'm asking that if a series is absolutely convergent, is not absolutely convergent, does it imply it's not conditionally convergent?
No,
No. Why is
it
that true?
doesn't. Uh, you can consider
So what is the relationship? Absolute convergence
absolute
implies
implies
conditional convergence, right?
that's it.
So therefore, non-conditional convergent implies non-absolute convergence, right? So why is it wrong what I did? Because I'm saying if it's not absolutely convergent, it implies not conditionally convergent. So it's equivalent to, if you take a contrapositive, it's similar as saying conditionally convergence implies absolute convergence. This is not true. So therefore, this is not true. Okay, don't do this mistake. Did you get this idea? This is a very basic idea. This is a basic contrapositive statement. So therefore, yeah. So how do you do this? As SK has told, by alternating series, right? So do you remember what is alternating series? Do you remember what is alternating series? Yeah, Rajshankaran?
If a sequence Bn is decreasing and limit n tends to infinity, Bn is equal to 0, then some -1 power n Bn will be convergent.
Is increasing or monotonically? It's monotone.
I said decreasing, right? Monotonically decreasing.
Okay. So it's following this, right? It's alternating. Yeah.
Yes, it is.
So it's minus order to the power n Bn. Bn is equal to 1 by root n. So by alternating series state, it's convergent. All of you got this? Yes or no? So absolutely convergence here. So just take 1 by root n plus n. Is this convergent or not? Is this convergent or not?
No, sir.
Why?
By P test, sir. R is less than 1.
Yeah, you're right. P-test. But how do you show that? Yeah, it's so essentially you can show that it's of course of the order 1 by order n. Sorry. Order of 1 by n. Because as n tends to infinity, n maximizes over root n. So it's order of 1 by n. And if anything is order 1 by n, it does not converge. Summation. How do you prove that? Let's not go into the order thing. I cannot do everything over again. But the idea is that we can just take you can observe that, let's say 2n. So 1 by root n plus n is greater than 1 by 2n. Okay. After a certain time, n will get over root n. So 2i n plus n is greater than or equal to root n plus n. So therefore, this is true, and this is non-convergent. This is not convergence. Hence, this is not convergent. This is convergent, right? So this is the order method, which is very important, and yeah, it's very important. It's done by this sandwich theorem idea. Similar here. So all these are convergent or not? Can you just tell me if yes or no? Yeah, and
So the third part, it won't be convergent.
the third part.
it will not be convergent.
Why?
Sir, if you separate it as 1 over n to the power 3 by 2 plus the rest of the terms there, the left series is convergent, but the right series is not convergent. As n tends to infinity, log n can be ignored with respect to root n.
I'm not getting you. So this is convergent. This is also convergent. We have proved it similarly here, like same as alternating series. This is by P test, P series. What about this? Log n by this. Can someone tell me? Is it convergent, not convergent?
Convergence,
How
sir.
do you show this? Why?
It is less than n by 3 by 2, sir. Log
What?
n by n, log n by n over 3 by 2 less than n to the power 3 by 2, sir. Will be convergent.
I'm not getting you. There's some network issues. Yeah. So how do you do this? Log n by n to the power k type of problems. Uska series. Do you remember? I also done this in our classes.
Using Taylor expansion of log.
How does that help?
We could get a polynomial form of log, and that might be easier to work with.
I'm just thinking about it. What you told, because it will be summation of an infinite summation. So that's where I'm getting the issue. You understand? Yeah. Any other ideas?
We have to find something log n. Like we know that log n is always less than n, but it doesn't give us anything because the upper bound, I mean, it will be
Yeah.
log. So upper wala thing is diverging, so it doesn't give us anything. So I need something that gives lower bound to log n. If I have to prove it divergent.
Yeah. So so log n is less than n. So what is the maximum power log n is less than equal to?
Sorry, I didn't get a question.
Just give me a minute. Yeah, and please go ahead. I'm just thinking about something.
Sir, if you consider if you use comparison test and that limit form, you can consider un to be log n upon n to the power 3 by 2, and you can consider bn to be 1 upon n. If you calculate the limit, I guess it will come out to be 0.
It's okay, but why is it like the limit is 0 does not say anything, right? Yeah. Limit of, let me just check one graph. Just give me a minute. Okay, so the basic idea is that log n is usually less than, some nth power, like n to the power. So you know that if you remember this limit n tends to infinity, log n by n to the power k, any k. So if, or log x by x to the power k. So if you do it by L'Hopital, you will get one by x to the power 1 plus k. So as long as k is greater than 0, as long as k is greater than 0, k is greater than -1, this will go to 0 if k is greater than -1, right? So therefore, in the long run, you can see that x to the power k for k greater than -1 surpasses log x. That means it goes above log x. For any k greater than -1, right? Go above log x is like this, and it will go like this, even if it starts below. So let me find out one example. I'm just trying it out. Yes. Or am I right or not? Just give me a minute.
Sir, if we consider k equal to 0, it won't, right?
Okay, then I have done some mistake. Just give me a minute. Oh yeah, I'm so sorry. I've done it a mistake. So it's k times x to the power k minus 1, and so it will be k. Yeah, so if k is greater than 0. If k is greater than 0, yeah, right. Got it? Does it make sense? So I didn't differentiate the below. So that's why it was wrong statement. For any k greater than 0, x to the power k surfaces log x. Right? Just let me think. Give me a minute. Just give me a minute. I'm just doing something for you. So if you take the function x to the power k minus log x, if let's say you differentiate it, at 0 it's what? At 0 it does not make sense. So let's do f dash x, you get k into x to the power k minus 1 minus this. I'm getting one sweet spot, so I will show you what I'm thinking. So if you just do the drawing of x to the power k, and if you just do a slider, I will tell you what's happening. So for yeah, so actually I don't know it's true or not, but for k equal to 0, fx is equal to 1 minus log x. you know that as x goes to infinity, this goes to minus infinity, right? And therefore, if you take x to the power some k or epsilon minus log x, this will also go to minus infinity, like for a small change from 0. Okay, from x to the power 0, say it will also go to minus infinity for some time, and you can show it on. I will show it here, let's say. So you can just think about this. Okay, it's interesting to look into this. So can you see the screen, guys? So if you have 1, it's like this, and then you decrease, 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 decrease. All of this are good, all greater than 0. But when you go to 1, 0, then it's, you can see it's less than, it's becoming negative. It's becoming negative. So as you small increase slowly, it's also becoming negative, negative, negative. The question is that, is it going up after some time? Is it going up after some time, or it's going down? So that's the question. But after a certain time, it will go above as n changes. Okay. So therefore, it's a slowly gradual change that's happening. So think about this. What happens? So this is very important. I like to show this when I teach. Like always, graph and all these things are very important. Okay. So I like to show these things. And so think about it right now. Just give me a minute. I will just share the screen. So therefore, the problem is this, that for this problem it's solved. For this problem it's solved. For example, if you take root x, or not root x, let's say x to the power 0.4 minus log x. Okay. Or let's say 0.5 minus epsilon minus log x. You can easily show that f dash of x is nothing but, let's do it 0.4. 0.4 times x to the power minus 0.6 minus 1 by x. So you get 0.4 times x to the power 0.4 minus 1 by x. Okay. So you can observe that it's always greater than 0. Is it always greater than 0 or not? Is decreasing or increasing? Can someone tell me? The f dash x is decreasing or increasing? So you can show that 0.4 x to the power 0.4 is greater than 1 if you take log x, or it's just x greater than. So after this number, it's increasing, right? So, and at this point, you can put in the value, we'll get, as x tends to infinity, it's increasing, we'll get that it's greater than 0, okay? If you put this value, we'll get it's greater than 0. So therefore, you can show that x to the power 0.4 is greater than log x by this method. And therefore, 1 by log x is greater than this. Sorry. Therefore, x to the power 3 by 2 greater than this. So therefore, you can show that log x, log n by n to the power 3 by 2 is less than 1 by So it's 1.5, so it's x to the power 1.1. And you know that summation of this exists, right? It's integrable. Right? All of you understood this, yes or no? It's all about understanding how log behaves. So today's homework, you should do this at home, that how this x to the power n minus log x behaves when it's increasing, when it's decreasing. Okay. So first step is you do f dash x. For f dash x, you get x minus 1 by x. This is the first you get. And then you check from here that it's greater than 0, greater than 1 when, greater than. So it's also equal to 0 somewhere. So when it's happening, what's happening? Okay. Check about all this. Check all these things. N can be anything greater than 0. When it happens, what happens? Check all of these results. Okay. When it's increasing, when it's decreasing, there's a one minima. So check this function and understand this function today based on n. And therefore you will see that you can therefore this inequality, whatever you get, will be very important for your exam, because you will get a lower bound, and you can use the lower bound while solving this problem, or upper bound, not a lower bound but upper bound, and a lower bound both. And you can get that upper bound, and you can send it to me personally or in the group, that what happens when x to the power n minus log x, for which n. We have seen that visually, but you have to do it mathematically right now. This is fun. You can use Desmos and other things to check your results. Okay, check when it's increasing, check when it's decreasing, whether it may happen that initially it shows decreasing, then it increases and goes to infinity. Okay, so try out and find out this function for n greater than 0. That's your homework for today. Okay, it's kind of a research problem for you, so check out this, and that will give you a lower bound and upper bound to log x, or maybe upper bound or lower bound, anything. So check it out, and therefore this solves our problem, right? So therefore this is convergent. All of you got it, yes or no? And similarly, this also solves our problem, right? So do this problem. This problem is really interesting, and I have done this problem on myself. So you should do it problems yourself too. It's an interesting problem. So this problem will give you a bound that how log x is an order of how, like, so summation of log, or either summation of log x is of the order of, do you know, summation of log x or integration of log x is of the order of 1 by n. Summation of log n is the order of 1 by n. That is easy to know, right? Summation of log n is the order of 1 by n, because if you do integration log x is 1 by x. So summation of log n is the order of 1 by n. So, but what about log x? So you have to know a good bound. So think about that. Okay. Okay. So that's it for today. Okay. So that's it. Okay. Thank you guys, and thank you for attending. And I will see you in the next video, next class. Stay tuned and stay blessed. Bye bye.